Okay, so next topic is about pixelization and quantization. So we will revisit these ideas we already know, but we will revisit this spatial quantization and intensity quantization. So yeah, so let's say that we have picture and then we want a certain region to have a smaller information content. So here the pixels are bigger somehow, and here in this area the pixels are small. So let's see how to do that. So this is a reminder of these ideas of pixelization and quantization. So we have a high resolution image. So now this is already in the computer. So this is a digital image, and then we have the pixelated image, in which what we see is that what we are doing is increase the pixel size. So now the pixel size are bigger here. Quantization is changing the steps in the intensity. So you see here the intensity steps are smaller, and here we have fewer colors. So let's say that here we have 256, here we have only 16. And then we can have both effects. So a quantization in space and a quantization in intensity. So this is the mind of that. Okay, so we start already from digital images. So this is digital, and then what we will do is an averaging. So what we presented this concept in the first time with this image being continuous, and then producing discrete image. But now both are discrete. This is this. Okay, so let's see a little bit this multiplayer. So let's say here. So we start with, let's say, this image. That is 4 times 4. So that's 0, 1, 3, 0, 1, 3. And then what we want is to produce a new image. That is this one. For this new image, now is 2 times 2, so 1, so 1. But we will call this one the downsample. Okay, so this is 5. And this will be the downsample image, RC. You recognize these RC as not this ones. And in our notation, the correct notation is with the square brackets because both are discrete. And then the thing is, how do I produce these values? These values, all these values here, they go. So I have to make. So let's say that I'm doing a downsampling by a factor of delta. Okay, so in this example, delta is equal to, we are taking 2 by 2 squares and we are producing a new image. So will be this average. Okay, so how do I express that average? I express that average. Okay, so it will be an average, and this average, because we are making steps of delta, will be delta squared. And now I will do it. This is a sum over the black pixels. Just to make it clear, it will be this one. So we will see 1, and then I of RC. So we are summing over this image. We are completing this average. This will be the value at 0, 0. So the value at 0, 0 is that. This is clear. This is just a simple example of just averaging this one. Use this value. And in general, we have the equation here. So in general, If I want to produce a pixel RC, what I have to do is go from the pixel R delta C delta to and take a step of delta. So the step of delta is R plus 1 times delta minus 1. If you particularize for 0, 0, then you have the expression that I had in the white book. And then this is the input image. So this is the black one, this is the red one. Okay, so now we have this downsample image. We have this small one. But what we want is to recover one that is again it's okay. So now I want to recover one that is at the original size. It's again 4 times 4. But now what happens is that this pixel value is replicated 4 times. So I come back, but now these 4 values are exactly equal. So this is the downsample image. So when I go from here to here, I am downsampling. I go from here to there, and the downsampling of the downsampling or upsampling depends on what is the pixel size. So pixel size here, let's say that we start the pixel size that is t. So we keep this pixel size is delta t, that is twice bigger. And now, when I do the upsampling, the pixel size is again smaller, is again t. But when you do a downsampling, you are making your pixel size bigger. When you do an upsampling, you are making your pixel size smaller. Yes, we fine. So now we will take this image, and this is the way to express this upsampling. So if we put this operator by a factor delta, and then we are back to the original size. So here you have an example. So let's say that these are the big squares. So these are the 2 times 2 squares. There's this 2 times 2 squares. I am replacing all the values here by the same value. So here we don't see the downsample. Downsample is going to be smaller. So we are starting with a given image. We don't see the pixels because they are very small, but you somehow see them here. And then this downsampling is not by a factor 2. It is by a factor, I don't know, 16. So we are going to an intermediate image that is 16 times smaller in each direction. And then we are doing the upsampling and we are substituting the values in the downsample image, and we are putting them in all these 16 times 16 squared. Okay.
The right is also
No, it is these two. So we are seeing these two. We are not seeing this one. We are seeing these two. So you start with something, then you compute the average of all these 16 times 16 pixels. You have one single value. Then you replicate these single values many times. And this one is called the pixelated. Here we have a zoom how this looks like. So we don't see the average value, but we have a block of 16 times 16 pixels, compute the average, and then we substitute all the pixels by the same average. And then we have these operators, so this downsampling, downsampling operators, this one. And these are the same names. These are the same names that you know for signals. So in signals, you also know these operators. So let's say that I have an image, downsampling operation. Let's say this is R. Downsampling factor then. So in signal, if it is a one decimal, so you know that you have signal, yeah. Same. X, right? If you do a downsampling by a factor of 2, you are taking this one. So in N, so let's put numbers here. So this is 0, 1, 2, 3, in the original space. But in the new space, this is sample number 0, this is sample number 1, sample number 2. And the relationship in the two is that the downsampling at the notation N is X of delta N. And if you look at these numbers, seem to be correct. So the red sample at 0 is the black sample at delta times 0. That is also 0. The red sample at 1 is the black sample at delta times 1. That is 2. So this is the downsampling operator. And you know that downsampling has a problem. It's the problem of downsampling in general. Very easy. So before doing that, or doing this operator, you have to put, I'm putting it with one the signals, but it is the same for the communities. Put an anti-aliasing filter. Then we have extruder that has the same simple pixel size. Now you put the downsampling by factor of delta. Now you have the downsampling. And this downsampling operator, anti-aliasing operator, what is it doing? It is removing high frequencies. You know that when you do this operation, what will happen in the spectrum? So let's say that I have a spectrum. Like that. Check out. So you minus 2 pi. So when I do the downsampling, what will happen with the spectrum? So what is the operation that will make this to have aliasing? Will be bigger. Okay, so it will be expanded. So this will expand. This will expand. And this one will also expand. Right here, minus 5. You have this as aliasing. This is the aliasing here. This overlapping is the aliasing. So you don't want that. So what you do is you apply your anti-aliasing. So this filter here will be the anti-aliasing. So the anti-aliasing is cutting by, in general, at pi divided by delta. So that when you make the expansion, now, with the anti-aliasing, you don't have this aliasing anymore. It is raw. It's fine. Then you have from the then the anti-aliasing is this one. It's the filter and the frequency response, the anti-aliasing. So this is the ideal anti-aliasing. So let's look at again what we are doing. So we are, so anti-aliasing filter is a low-pass filter. So what are we doing with this fabric? This is a low-pass filter. So this operation of taking all pixels and average is our anti-aliasing. It is not the ideal one. But it is a low-pass filter that is preventing the high frequencies to overlap to match. So this averaging of 4 times 4, this operation here, this operation within the average is anti-aliasing. So first we do the anti-aliasing. This is the average. Then we make the downsampling. In this expression, both are done at the same time. So first we do the anti-aliasing, and then we are just taking one sample, one average of value. We are doing both at the same time. And then we have the upsampling. The upsampling, you may remember from one deceiver that upsampling was the opposite. So the upsampling had a downsample signal. You had the upsampling by a factor 10 factor, and then you had not an anti-aliasing filter, right? It was for a reconstruction. Then why this reconstruction? You need a reconstruction because let's say that now my signal is this one, the downsample signal this one. Stop sample and you have values here. And then this one that I will call green. So this one doesn't look like. So it looks like this. First one I copy, and then I have 0, then I copy next one, and then I copy next one, and so on. This one X, even that, and the relationship was something like this. Equation, something like that. So it would be X dx of n divided by delta if n is a multiple of delta and 0 are. Okay, so let's see. We have sample number 0, 1, 3, 4, 5. So sample 0 is a multiple of 2. So I have to do 0 divided by 2, that is 0. So I'm taking this one. Taking this. And then x tilde of 1. X tilde of 1 is not a multiple of 2, so it is 0. X tilde of 2 is a multiple of 2, so it will be 2 divided by 2, that is 1. 1 stick from this one. And here the axis is 0, 1, 2. Okay, so this is my upsampling operator. So this is my upsampling operator. And now this signal is not to affiliate. So it has value 0, value 0, so on. So we don't want that one. So what we do now is to convert this one. Or convert this the reconstruction filter. Which was the reconstruction filter that you were using so far? The SIG. We're using the SIG to reconstruct the signals. And here in this case, we are not using the SIG. We are using this. So when I convert this signal with this signal, what I'm doing is just simply copying one value and copying it. So now we understand a bit more what we are doing. And now we understand it in terms of signal processing. So what we have done is, so this averaging, the averaging that we do when we downsample is an anti-aliasing filter. Then we have a downsample signal that is smaller. Then we take this smaller signal, we do the upsampling, but the upsampling is between zeros, and we are copying. So this copying is a reconstruction filter that is small. He's not explaining these operations in the way I have done it, but they are totally equivalent. So here we see the anti-aliasing and the downsampling at the same time. So let's see. So here we have, but this is for the bands. So we have an input image and rows and columns. And then what we are doing is the mean of these rows and columns for all the neighborhoods in the image I. So all the pixels in the neighborhood corresponding to the RC. So this, it is simply saying this operation here. Explaining is this operation. So we have an RC pixel. This is RC. Then you are looking for what is the neighborhood, the original image, this neighborhood. And this neighborhood would be indexed by row and lines. So for every pixel RC, you look in the original image, which is the corresponding neighborhood. And this is the neighborhood corresponding to RC in the original image. In the original image. So all these pixels here, and this is set. This is the set of values. Set of coordinates. And now we are computing the mean of that image in that set. We are saying here. And this is the set. It is a set of all the coordinates. That row is R is RS plus 1, so on, up to R plus 1 success. This is the this is a downsampling by a factor S. In our previous slide was a downsampling by a factor then. And the same for type. Okay, and then we have the upsampling. So the upsampling that we are doing is the pixelated image is at the location row carry is the downsampled image at the corresponding RC. And then who is this RC? RC. So we are doing them the opposite way. So instead of for every point looking what is the RC, what we are doing is for every RC, looking for what is the region that I have to copy. This region will be wrong time. By this the same neighborhood that we find before. So the neighborhood has exactly the same shape as this one. Then we are doing that something by a factor. Yes. Okay, so let's say let's make an example. So we will do 8 steps of downsampling. So this is the very last step. So here delta is 256, and then now delta is 128, 64, 32, 16, 8, 4, 1. Okay, so we start with the series. Now we do pixelization by factor 2. Now we're making this blocks size times 2. But we can make it size 4 times 4 or 8 times 8. Now we start to see these blocks. For instance, 2 times 2 you barely see them. So this means that very often the pixel size that you have is too small. Very often you don't need such detailed pixel size to see an image with sufficient quality. Then as you go down, at some point it becomes very, very flat. This one looks good. Any questions here? Okay, so then we will move to the next question, that is quantization. So now we will also increase the pixel, not the pixel size, but the quantization step. And now in the first case, and here we see an example. So here we have an image represented with 60 million colors. What is this 60 million colors? Why 60 million? No. No. An RGB. So RGB, 8 bits for each one of the channels. And now we will have only 16 colors in each one of the channels. So what we are doing is increasing the pixel size, or not the pixel size, the quantization step, but now in intensity. So let's say that we are going from 0 to 255, but now we want to go in 16 steps. So now my steps will be, of course, bigger, so it will be of size 16. So I can either represent value 0, or I can represent value 16, but I cannot represent the values in between. So I represent 0, 16, 32, 48. So these are my values that I can represent. And we can do the same as we did before. So let's do it with 8 bits. So with 8 bits, we are going in steps of 1. So I have all the 256 levels. If I do it with 7 bits, I'm going in the steps of 2. Okay, so I either I represent 0 or 2, but I cannot represent 1. And then I have only 128 different levels. Or I can go in the steps of 2 or of 4. Now I have only 64 levels. And you see, also in intensity, it seems that we have the same behavior as the pixels. So very often we have very fine steps in intensity. So here I barely see any difference. If you are going, this one has 4 times less information than this one. At some point you start to see the difference. So this is very obvious here. We have very flat regions. Originally they were not so flat. And here it is just a very extreme case, just for reference. And here are our grayscales. So if you use 8 bits, the pixel size, what is the intensity step? The intensity step. So the intensity is there. So I have to go from 0 to 256 in, let's say, I'm using n bits. I'm using n bits. How many different values I can represent it with n bits? How many different values? To the n. So I have to the n values. So I have to distribute, let's just go to columns here. I have to distribute these 2 to the n values in this axis. So I have to go from 0 to 256 with 2 to the n values. So what is my step? My step is 256 divided by 2 to the n. So let's say that n is 3. So if n is 8, then is 1. I'm going steps 1 from 0 to 256. And actually, if I count 0, my last value is 255. I cannot reach the physics. And let's say that n is 1. So if n is 1, step 1. Yeah. So let's n is 1. Is now I have this value, but then my next one is 128, and my next one is 256. But is beyond my representation. So my intensity values, the values that this signal can take, this belongs to the set. Belongs to the set, say I delta. I use the values. 0, 1, and so these are the possible values I can take. So, for instance, in the green one, so in the green one, I can take values 2, 1, minus 1, 1. So I can take the values I delta I 0 to 1. And delta is 128. So I can take only the value 0 to 100. So now what we are doing is the same idea of sampling, but now we are sampling in the intensity space. You see that the kind of the kind of expressions we have are the same ones that we were having with the spatial sampling. The spatial sampling. So we are also having, or we are going in a step of delta, the S here in this equation. We are going in the steps of delta, and we go up to whatever minus. Okay, so these are our values. So now, okay, 1 bit. We will be able to get only 2 values. Let's say that you want to represent this scale. So let's say that you are allowed to take only 2 values in this scale, 0 to 256. So in the standard sampling, these are our 2 allowed values. Do you think these two values are very representative, or you are only allowed to take two values between 0 and 256? Would you take these ones, or you would choose other ones? I would choose ones that are more in the middle. I would choose these ones for the view. Because they are more so let's say that you have steps of one. So I have a histogram here, my values, my image. So now let's say that I take only the green values. I take the green values. What is the error between any one of these values and 0? How about these errors? And I say, how about these errors? And now let's consider the errors. But I take the blue one. I have all these errors. Then I have all these errors. Which one of the two do you think will be smaller? For these, the expected value of the variance of the error divided by 3. What is the expected value? The variance of error by blue. Which one of the two do you think will be smaller? The blue ones.
We're gonna have less contrast. Yes, the woman and.
Good question. So you will have less contrast. Contrast is the difference between minimum and maximum. So in the green scale, the distance between minimum and maximum stays. The blue scale, the difference between minimum and maximum is this one. They're equal. So I will have the same contrast. Okay, so now let's say that I do the blue pixelization or the blue quantization. I'm still allowed only, this belongs to, I'm still allowed to take only two values. So I is 0, 1. But that is a better sampling. So a better sampling is 1. So I will not take the green values that are these ones, but I will take the blue values that these ones. And the blue will have this is that error. So that representation error will be smaller in the blue rather than the green. The trick is this one, this class delta. And this is what we are seeing, this gray state. So this gray state. So if we go through the green sampling, this would be 0, and this would be 128. But we can also make it be 64, 928 plus 64. Then the same here. So now we understand we have steps of delta, but my sampling doesn't need to be aligned with 0. It can be in the middle, can be shifted. And if I shift it, I shift by delta hat, I'm reducing the representation error. Okay, so here we have our intensity scale. And so this is the green. So green. And also, for instance, you can take these values, 2 bits. Take this one. So, which in general, this is referring to how you choose. You will be only with 2 bits. You are only allowed to have 4 values. Which ones to add? You have is defined by this set. So you have to define which is the set that you really want to use as representatives. And this is kind of arbitrary. So you can think of this one that is very simple one. You can think of this one that is minimizing the representation error, or you can think of any other one. So actually this one doesn't have any special property, but you're also allowing just for values. So the key idea here is if you are only allowed to use 2 bits to represent your images, you have to choose a set intensity that you can refer to. And when you say 0, 0, 0, 0 is this one, 0, 1 is this one, 1, 0, 1, 1. You are choosing 4 values, whichever you want. They can be the green ones, they can be the blue ones, they can be the purple ones, whatever you want.
That doesn't mean that 0 and 120%.
Yeah, so here 0 and 1, assuming that n is equal to 1. And when I go to 0, 2 to the n minus 1, I'm just giving the example with n equal 1. Sí, si yo hago que delta sea 128 y la i vaya 0,1, porque los dos valores que puedo representar son 0 y 128. So now what we are saying is you have to quantize a space, and now with this part you can also quantize intensity in different ways. And here we can have these ideas. Okay, so let's we have an original image, and now we do the contrast enhancement. This contrast enhancement we already know, so we'll this is just taking the minimum to 0, the maximum to 50. This was one of the first operations we introduced. But now I can concentrate on different parts. So, for instance, I can take why cannot I have the original image between 0 and 255. And now I can say, okay, I will divide this into parts. So originally it had some histogram. And I will divide this into. And in one of the spaces, I will put the sampling one of the sides, while in the other one, which I will use. So my distribution of levels doesn't need to be homogeneous. So here we were going in the black scale. All my deltas, they were all equal 1. And I had at the end 56 values. But I don't need to be like that. So I may say, okay, from here to there, I will only use 64 values. And the remaining are 156 minus 64. All the remaining, I will keep for this one. So now my sampling here will be 1.5. So now we are generalizing our sampling now in intensity.
Different areas, it's different supplements.
Because here you have an example. So for instance, let's say that I do a find this image is very dark. So this image is dark. So if I put the final sampling in the dark region, so just the opposite of this one. Now my fine sampling is here, here. And then I rescale. Now my image becomes brighter. It depends how many levels you have to represent your information. So if your information is dark, so let's say that my information is like this. So the gray value, this is the histogram of the image type. This gray value, let's say that it is something like this. Where would you put more samples? The low area. I would put a lot of samples here, and then fewer here. Because I don't have so many. If you then think of them in terms of errors, when I compute these errors are small. When I compute these errors are large. But I have so few values with large errors that I don't care. So now you can adapt your intensity sample where your information is. So if your information is dark, you should put more sample in the dark area. And when you rescale, then you have something like this. And this is the opposite. Okay, so this is the dark region is enhanced, so you have more samples. Here the bright region is enhanced. So you have more samples just in the bright region. The rest of the image then becomes dark. This we wouldn't like this one.
Because more sample
In the bright area. Then all the rest becomes in the dark.
that's why the right area.
Just to illustrate what happens. Okay, so if you want to deal with this, you can probably will want this application. And then this is enhancement when you have 8 billion with 16 billion. So now you allow even fine samples. And then we have here right. So we will see the system. So let's make a break of 10 minutes. Bueno, pues si no, vamos a ir. Okay, so here we have the histograms of each one of the different images. So, and with two different quantization steps. So one is with 8 bits, the other one is with 16 bits. So here we have the original. The original is goes from 0 to 55. And then we have the different versions. So when we do contrast enhancement, and we understand these zeros here, these holes in the histogram, they're coming from the values that cannot be achieved by the transformation. And we see that when you do it with 8 bits, there are many values you cannot reach. But when you do it with 16 bits, so you do the operation in 16 bits, and then you come back to 8. And now you reach all of them, the same with all the others. Okay, and even these values that were collapsing. So why this is why we have these spikes. This doesn't have with 16 bits. So this is a general approach to processing. So it is you have an image. So let's say that you have an image with 8 bits. Now you do an intensity Now you do your transformation. And you come back with. So this is a very general scheme. So you start with an image with a given step size in intensity. You double it. Now you have more precision. You do your transformation and then you come back. And you see that the histograms, all these problems that we were having in the histograms, like having zero, having spikes, now they disappear. Because you do the operations with higher precision.
The transformations are for a consider decreasing the value of intensity.
Yeah, so not increasing or decreasing, but decreasing or increasing the intensity step. So now you have an intensity step that is, so let's say that here we have 1, delta 1. Here we have delta. We can go in the steps of 0.5. This is also 0.5. But then when you do the downsampling, go back to 1. That's what is delta prime. So you do the operations with higher precision, and then you come back to the precision that you had originally. Yeah, so for instance, let's say that we have this image, and now when you do the enhancement with 8 bits or with 16 bits, for the one with 16 bits, I would say the quality here is a bit better than this one. It's hard to say that. Say it is a little bit better. And numerically, you know, it has to be better. And here the histograms, original, and then when you do the enhancements in only 8 bits, you do the enhancement with 16 bits. And yeah, now we can.
And I think it's why if you have a zero and then one.
Yeah, so this is coming from. This is from the first lectures. So let's say that you have an operation. Let's say that my contrast enhancement is multiplied by 2. So, my contrast enhancement. Now let's think of the values that we could have. So now we have I prime and I. So I will take the value 0, 1. And what is my I prime value? So I have to multiply 2 and have 0, 4. And in the green values, the green values, I don't have 1, I don't have 3. So you have a histogram at the beginning. You will transform your image. You have poles. So you will have some number of pixels with value 0, and then no pixel with value 1, and then some number of pixels with value 2, no pixel with value 3, and so on.
Why?
Yeah, because I will have the same effect here, but now let's make my image. Let's make it with 16 bits. So when I do it with 16 bits, I still have this effect of having zero, but then at some point, I will use I second. And I second is I second. I second is half I prime. And now I have, and why I have? Because if I want to go this mother half is we will have to think the factors. Okay, so when you do so let's say that I want to multiply by a factor. So this goes from 0 to 5. Now this one can go from 0 to 5. But this is 16 bits. This is 8 bits. So multiplying by 2, the whole thing is 9 bits. So 9 bits is not a fully exploiting this way. Okay, let's do it this way. So I have I. Now I multiply by 2. This is my operation, but this is 8 bits. This is 9. Now I will do an operation to scale it to 16 bits. So which is this operation? This would be 2 plus 16 divided by the 9. The previous one. Say I. This is my prime. This is I second. I multiply the previous one. And this operation is scaling up to 16 bits. Okay. And now I want to come back. Wait. Which is this operation? It's 2 together. I the 16. I said. So my contrast enhancement is here. But all the others is just to fully exploit my range. Which one? This one? This is the contrast enhancement, so it is the same operation. But now I'm not fully exploiting my range of bits. So I make it, I scale it to have my full range. And then because at the end I want to come back to 8, I do the similar operation. And I have to round. So round this. Rounding. ¿Por qué te hace?
Porque no le hace tener eso.
Claro, porque yo me llevo esto a utilizar los 16 bits completos. De aquí estoy dividiendo por 1 partido por 156. Esto me da mucha precisión. Este factor es 1 partido 256.
Pero quedan menos producción. Que con la posibilidad feliz tienen menos producción.
Claro, tengo menos precisión, pero como antes me lo he llevado a 16 bits, estaba ocupando un montón de valores. Cuando divida por 256, voy a tener un montón de fracciones. Y luego ya redondeo. Pierdes la información. Pero no te quedan huecos. Okay, let's see this part. So I have an image. So once for a value, I have the RGB values, and each one is represented with labels. So this is B. So originally they have 8 bits. And now the new one will have I should be in 4 parts in 2 parts. And now, what we will just to see the 4 bits, the 4 lower bits. So I will replace each one of the values by 0. Then 4 bits that you have before. It's 4 bits you copy, the other ones you set to 0. Now we look at this image. This will be a new image. This will be a new image. And I look at it. How does it look like this? So it seems that in this image, when you look at the 4 lower bits, most of them they don't contain any information. And only this region here will contain some information. But otherwise, in the rest of the space, there is no information, it's just noise. Okay, so now let's do something. Okay, so let's say that I have an image. Okay, and this image has 8 bits. And I will change from 8 to 6, and then let's see the difference. So this is originally this is with 8, this is with 6. So let's see how we have done this. So okay, I have these values, but now my decomposition is different. So my decomposition is decomposition is 2. Then I construct my new image. That will be here 0, here this 0, then this 0. Has to be correct. These are vectors. This is 0, 0, 0, 0. Yes. But these values are this one. Simply copy those bits. And then you have any of it. Your new image where the 6 first bits are the same and then the last 2 are similar. So this is the original with the 8 bits. This is the new one with only the last 2 bits, they are set to 0. And you barely see a difference. Why? Because we saw that the last bits, they just contain noise, or they don't have any useful information. So if you put noise or you put zeros, you don't see the difference. And here you have the histogram of the 2 images. So this is the original, this is the new one. Why this one didn't pass holes? Because with only 6 bits, which is the first value that I can represent. Also is first value is this one. This is value 0. The next one that I can represent is this one. Value 4. The next one is this of 1, 0. And this is value 8. So I cannot represent the values 1, 2, and 3. That is why we have these gaps in the values. Okay, this we understand. Very good. And this is how you can do that. So let's look at this part. So this part is you take the image, so the byte, so you take the band of that image. You do a right shift by 2 bits, and then you do a left shift by. Let's see how that works. So let's say that we have 8 bits of the first bit. Let's say that we have. So these are the 8 bits of the first pass. This one. And now I can write it by 2. If I do it right by 2, and what do I get? I will get it's this 0. I don't have anything to shift from the right. Then with 7, 8, 6, 5, 4. Now you have 8 bits again. Now you do the left shift by factor 2, by 2 bits or so. Now this is what we get. At this point, having 7, 6, 5, 4, 3, 2, and 3. So with this bit movement, we can very easily get rid of the last 2 bits. So this is this branch. Okay, now this branch. So now instead of 1 image, we will have 2 images. The second image, we will do a right click by 6 bits. So have another image. Image 2, and then have the 7, 0. We do a right shift by 6 bits. We have here 0, 0, 0. Okay, just the first 2 bits, they have shifted the right. And now we have this 2. This addition is and so. So we have these were coming from image. These were coming from image. Then you do the XOR between the 2. Yeah. 7, 5, 6, 5, 4, 3, 2. Now we need 1. Then we have B7, B6, normally. So the first 6 bits are coming from image 1. The last 2 bits are coming from image 2. We are taking the most significant information of the upper bits of image 1 and the upper bits of image 2. And then this is the XOR. Then this is our result. Now we are operating at the level of bits. Okay, so here we have image 1 in the upper 6 bits and image 2 in the lower 2 bits. Okay, so let's say that I want to recover from here. So this is my result. I want to recover image 2. This is the operation I have to do. Left 6. Left 6. Then what I have is 76. 1. What I have. And now I have recovered image 2. So now you take this output. This output here. If you do left 6, you recover whatever was left from image 2. Okay, so this is having the 2 of them. Now we do left 6. What do we get? Okay. Okay, so in here, we have two images. One is this one, this picture. The other one is this one. And both were displayed together, but we don't see the second one. We don't see this one. Why? Because it's in the lower bits. We are not sensing the lower bits. Our eyes pay attention to the highest bright point. And this is too weak. It is there, but it's too weak variation, and we don't see it. And we can extend this idea with four, and 6 pixels, 6 bits. So we right shift with 4, left shift with 4, and then, so the first bits are coming from image 1, the four last bits they're coming from image 2. So for instance, this is image 1. This is image 1 quantized with 4 bits. So the lowest bits they are 0. You see? Okay, there is a loss of contrast. Otherwise, it looks similar. Now it contains the two images, so image 1 and image 2, but we don't see image 2, and this is image 2. So this image here, contains first 4 bits from this one, second or last 4 bits from the other one, but you don't see the trees here. Yeah. So this contains this word and the trees. But you don't see the trees because your eyes are not sensitive to trees. So this technique is called steganography. So steganography is stegan means hiding. So it is hiding an image into another one. And this is a very simple way of hiding an image into another one. This is a very simple way of hiding an image to another one. Why do you think it could be useful, this hiding information? Encryption. I think that would be great amazing. What application do you think is copyright? If you want to copyright, then what you can do is you just to add, you don't need to do it in the whole image. So you can take a corner here and put a value. That's it. You can very easily check whether this is your image or not. Okay, so any question after here? And then this idea of applying different transformations to different parts of the image. So let's say that we have this original image with 16 bits. And then you can do, you can look at which are the darkest parts. So these are the darkest regions. And then you apply the darkest region, you apply the transformation in the brighter region, you apply a different transformation. So what we are doing now, we are separating. Taking an image. Mask 1, mask 2, and then in mask 1, you apply one transformation. Mask 2, you apply another transformation. Now you are text. And how to define this mask? In this example, these masks were defined in terms of bits. Okay, so not in terms of bits, but So, anyway, in terms of the histogram. Any histogram. And you have some histogram. Then you define your mask according to this is mask one. So all the pixels with these gray values we go through mask one. And then all the pixels with this gray value they go mask two. Then you apply two different transformations and then you add. This is we apply a transformation to the dark pixels, another transformation to the bright pixels. Then you add the two. For now, you have the benefits of both. Okay. But now you see that you can be very creative about how you treat your images. So very creative on how you construct your systems. Okay, so we have seen that normally adding noise is not a good idea. So noise is something that we want to eliminate, not something that we want to add. But then there is a particular application where adding noise is useful. So it is when you want to reduce the number of gray values. So let's see an example. Okay, so let's say that you have this image and you have it with 8 bits, but you want to represent it with 4 bits. Why you may want to go from 8 to 4 bits? Which application will environment may want to have less information rather than more? Let's say that you want to transmit this image, and the bandwidth of your channel is limited and have as much bandwidth as you do. Or you have to pay for the bandwidth, or to pay less for your transmission. So you can transmit this one with 8 bits, and then it goes with whatever. If you transmit half the information, it is twice cheaper. Okay, so it might be that we want to add noise before quantizing. That is with 4 bits, you don't really notice the difference. Let's see with 3 bits. 3 bits is yeah, you see the difference here. I think it is more obvious with 2, even with 1. With 1 is with 2, you see this person here is very artificial. So it is just 2 bits, and we know how to do it with the right shift. So we are transmitting 2 bits per pixel, but when you add noise, it looks much more natural. Okay, so let's see. So the quantization we already know. So quantization is just taking the number of bits that you want. So even you are not restricted to integer number of bits. We will discuss that later. But before quantizing, you add noise, and you add noise with 0 mean and this standard deviation. That is n divided by q. N is the maximum value of the image. This image has maximum value n, and you take maximum value divided by q. Q is the step that you are taking. So if you take this sigma, and you generate noise with 0 mean and sigma this one, halves, and then you quantize. And then you see that the result of the quantization is much more natural if you add noise than if you don't. This is kind of extreme. But just transmitting 1 bit per pixel okay, the quality is not good, and this 8 times cheaper than this one. Okay, so what is this quantization? So quantization operator. Value. And we quantize this value by factor Q. I prefer that. This is a matter of notation, but you have to be consistent with our previous notation. And apply this line and then you produce like line. Okay, so I prime is delta I is bounding of I divided by n. This is this quantization. Okay, so let's see. So let's say that I takes a value of 0, 1. I prime the quantization factor 2. So delta is 2. Okay, so which are the values that we have? So would be 0 divided by 2 round. So let's say that our rounding is always down. Okay, our rounding down. This is a notation. We have 4 ways of rounding. This one, this one. So this is one. This is floor, rounding down always the closest integer from the top. So this is silicon. Let's put this examples. Bound of 0.7 is 1. Floor of 0.7 is 0. Okay. And the ceiling, I will change the 0.3 is 1. So you have to get the next integer from above, from below, or the closest one. So let's say that ours here, ours is rounded up. So which are the values that we can take? So 0 will go to 0. 1 divided by 2, round down to 0. 2 divided by 2, round down to 1. This is this quantization. So if the input has value 0, you quantize to 0. If it has value 1, you quantize to 0. If it has value 2, you quantize to 2. So, and then the delta, if you have 3 bits, you have, in general, you have n bits, delta is to the n. This quantization that we are saying here, 4 bits into the 4. 3 bits, the 3. Sorry. 8 minus. I want to leave only n bits. Okay. The rounding. Yeah, so rounding is finding the nearest integer, but the nearest integer would be the one that is really nearest. This is round. The one that is nearest from below, the one that is nearest from above. So adding noise, and this adding noise is dithering. Dithering is this operation. It's this operation in which you have an image, you add noise of this. This Q is my delta, okay, in the whiteboard. Yeah, actually, there is a small mistake here. Q is not the number of bits. Q is the delta. And then you quantize, you produce an image. All these operations is called dithering. Okay,
Use the delta set.
sorry. Q is delta, yeah. In this expression here, Q should be delta. So Q is not the number of bits. It is 2 to the n, 2 to the 8 minus number of bits.